So in this lecture we will study about a very important term that is called as dimensionality problem. So what is called as the dimensionality problem? So we know that if in this data analytics we are just constructing or designing a classifier or predictor, okay, which will classify the items or the groups by using the prediction rules or the algorithms, okay. So for that we don't need to just make it more complex. For that we have to reduce the dimensions or the features, okay. So we have to use less features, and our main goal is to use less features by which we can reduce the complexity of the classifier and we can easily classify them, okay, by using less number of features or the dimensions. So let a object is there and it has some features f1, f2, like that, fn, okay. So the pattern will be represented by this using f2, f like fn. So these are the features, and we have to reduce it like p, that is totally reduced to like f1 comma f2 comma f3. Let's see, okay, where n is greater than 3. Getting? So here we have reduced it and we are finding a better model with less complexity, because the input should be less, the dimension should be less, and we are performing and we are giving good results to the user by finding the good patterns, okay. So basically our main problem is to reduce the dimensions. So here we will see how to reduce a 2D to 1D, okay. This is our main problem, okay, 2D to 1D, okay. So for that we will take an example. Let's see, okay, take an example for that, okay. Suppose two types of a 2D diagram is there. You can see here height is there, here weight is there, okay, and we have to just project the points of this 2D, okay. We have to just project the points of 2D, this 2D space, okay, space in 1D space. So for that what to do, okay. So for that we have to just convert this 2 dimension to 1 dimension, okay. So for that we will draw a line here. Getting? So how to draw this line? Means this line will represent, okay, represent the points or the features, the points or the features of height and weight in the new axis, okay. So how to find this line, or this line may be here, okay, because the variance of the points are going here and here. So we have to find the line here or here, so that the points of this 2D can be converted to 1D and they can represent both features points in a single line. Here we have reducing the dimensions from 2D to 1D, means 1D will represent 2D, okay. So how to do it? For that we have applied an algorithm that is called principal components, okay. So this is the most important term, that is called principal components. This is mainly used in data analytics, okay, for reducing the dimensions. Means before learning in a machine, we have to use principal components to reduce the dimensions or the attributes for designing a classifier. Then after that we can perform our classifier designing. Okay, so we know that to find the principal components, okay, how we can apply the principal components here. Okay, we will see it. Okay, so for principal components, okay, we have to use so here in this 2D problem, okay, we have two types of principal components, that is called first PC, okay, and second PC. So in this diagram we can see that the first PC will be, for example, this one. Okay, first principal component will be this line, and the line which is perpendicular to this principal component is called as the second PC. This is called as the first PC and second PC. So how to draw the first PC and the second PC, we will go through it. Okay, so the main problem here is to design the first PC. Okay, let's see. So in the first PC we can see that for that we will use a term that is called variance, okay, and eigenvalue and eigenvectors. So here we can see that what is the variance, eigenvalue and eigenvectors. Okay, so here you can see why we are going for this eigenvalue and eigenvectors to find the principal components, that will be first PC and second PC. Getting? So for example, what we are doing here, okay, so why we are using this eigenvalue and eigenvectors here. Okay, so first of all we have to find what is the variance. Okay, here we can see the points are varying in this region. Okay, the points are varying in this region means that we have to find a line that will go there, and the points are varying in this portion also, so we have to find a line here. So as the line is going here, for that we are using a term that is called eigenvalue and eigenvector. So what is the use of eigenvalue and eigenvectors? I am saying that. Okay, so eigenvector has a property that it will not change the direction here or there from a point. Okay, and it will go in a straight direction. That's why we are using the term that is called eigenvector. Okay, for example, okay, let's see. That's why we are taking eigenvector in this principal components designing. Okay, let's see. Suppose and it can be represented as ax is equal to lambda x. Okay, so ax is equal to lambda x. Sorry, ax is equal to lambda, where lambda is the eigenvalue and x is the eigenvector. Getting? So lambda is the eigenvalue and x is the eigenvector. So for example, what we will do now, okay, let's see an example of it. Okay, so for example, the value of a is 3 0 1 2. It is a matrix. Okay, and we are multiplying this matrix with a vector 1 comma 1, and it will give a value of 3 3. We know that. Okay, then how to represent the 3 3? 3 3 can also be represented as 3 1 comma 1. So you can see that the value of x is this, the value of x is this. So we are multiplying this with a term that is lambda. Getting? Means we will find a value 1 comma 1 from that from that matrix. If we are multiplying it with a value lambda 3, okay, then it will go. Then if a matrix is multiplied with a point, okay, suppose 3, then it will move in this direction also to the point 3 comma 3. This is the example. That's why we are taking the concept of eigenvector and eigenvalue, because they are not changing directions, they are only moving in these directions only. Okay, it has the property. That's why we are taking this. So we have to understand this concept. That's why that's why I have discussed this, why we are using eigenvalue and eigenvectors to just design the principal components. Okay, so let's see what are the rules, okay, and the steps, the procedure to design the first principal component and the second principal component procedure. So what is the first procedure? First procedure is to find the covariance. Okay, so how to find the covariance? Covariance is calculated by 1 by n, that is epsilon summation x minus mu into x minus mu whole transpose by n. Getting? So this is 1 by n summation x minus mu into x minus mu transpose n. Then the second point is finding the eigenvalues corresponding and finding the eigenvalues and corresponding eigenvectors, that is x is equal to lambda x. Okay, then the third is eigenvector corresponding to the largest, okay, to the largest eigenvalue is called as the first principal component, and the second eigenvalue, which is smaller, is called as the second principal component. Okay, getting? So these are the three rules by which we are going to find the first principal component and the second principal component. Let's solve a problem for that. Okay, for example, this is the example we are going through. A input set is given, that is two vectors, a vector is given x. Okay, this vector x has two values, x1, two features are there. We have to convert it to one feature, so that values are 2 1, let's 3 5, then 4 3, then 5 6, okay, then 6 7 and 7 8. Okay, getting? So our first step is to find the mean, that is mu. Okay, that will be let okay, in this example I want to say that whatever values I am going to add, that may be wrong, but you have to solve the problem according to the procedure. Okay, whatever values like 4.5 and 5 I am finding that may be wrong, I am just giving an example to you. Okay, so 4.5 and 5 I am getting the mean for this. Okay, means we have to find the mean by using 2 plus 3 plus 4 plus 5 plus 6 plus 7 divided by 6. Okay, that is 4.5, and 1 5 3 6 7 8 you add them and then divide it by the number of elements, that is 4.5 by 5 or 5. Okay, then the second one is find x minus mu. Okay, let the x minus v values are minus 2.5, minus 4, then minus 1.5, 0, then minus 0.5, minus 2, then 0.5, 1, then 1.5, 2. Okay, like the same, the values, okay, you can find x minus mu whole to the transpose. Okay, then you will just transpose this, like minus 2.5, minus 4, like minus 1.5, 0, then minus 0.5, like the same you do, minus 2, like that. Okay, so this is very easy. Okay, let's go for the next part. Okay, then after finding, then you have to do, after finding that, you have to find the covariance. So what is the formula for covariance? We have studied 1 by n. Okay, so summation of x minus mu, okay, into x minus mu whole transpose by, okay, by, what is the formula for this? Okay, so this will be by n. Okay, getting, so we have 1 by 6. Okay, then the values you just multiply them. Okay, multiply the single unit. Okay, x minus mu into x minus mu whole transpose, you just multiply and add these values. Okay, like x minus x1 minus mu 1 dot x1 minus mu 1, okay, whole transpose. Okay, this you find, then add it with x2 minus mu 2 dot x2 minus mu 2 whole transpose, like that you have to do 6 times. Okay, 6 times, then 1 by 6. Then this is, then by this you can find the covariance of a matrix. Okay, so let's see, let we find this by a covariance. A covariance is suppose 2.9, 0.33. This is the final ultimate result. I am saying 5.67. Okay, then we have to find the, after finding the covariance, we have to go for the eigenvalue and finding the eigenvalues and corresponding eigenvectors. So for that, let's do Ax is equal to lambda x. Okay, so this can be represented at 2.9, okay, 0.33, okay, into 0.33 into 5.67, x is equal to lambda x. Okay, so this can be represented like, okay, to find by finding the determinant, that is 2.9 minus lambda 0.33. Okay, then 0.33 5.67 minus lambda, okay, is equal to 0. Okay, then we have to solve this equation. Solving this equation by using the quadratic equation. Okay, we can solve this equation and we will find the lambda square value. Okay, because this is the determinant. Okay, and we can find the value of lambda 1 and lambda 2 from this quadratic equation. Okay, by solving this determinant, okay, let's see, we can get a value of, for example, lambda 1 and lambda 2 is 5.88 and 2.7. So our the third part of the procedure, it says that, okay, so the value of lambda 1 which is greater, okay, we will take this one as the first principal component, okay, to draw the line. Okay, let's use this by Ax is equal to lambda x and 2.9, 0.33, 0.33, 5.67, okay, x1, x2 is equal to 5.88, x1, x2, getting 5.88 into x1, x2. Okay, so by solving this, we will get some result like x1, x2 combination. Okay, and that combination may be like x1 is equal to 0.11 x2, like this, okay, getting, or x2 is equal to 9x1, you can get this also. So by using x1 is equal to 0.11 x2, we will draw a line, you can see here. So x1 is equal to 0.11 x2. So here if x2 is equal to 1, then x1 is equal to 0.11. So x1 comma x2 can be represented as 0.11 comma 1. Okay. So in this diagram, let's see, we will draw, it is 0, okay, and let's draw it 0.11 comma x2. This point can be drawn here, okay, drawn here 0.11, okay, comma 1, okay. So this is the first point, and we can change the value of x2 to 2. Then what is the result? Then you can find that you will get a point here, then here, then this will go straight, okay. So and this line will go straight. You will change the value to 2, then 3, like that, okay. And for the value of lambda 2, if we want to draw the second principal component, you will get the line here, okay. This is second PC, this is the first PC, okay. For second PC calculation, we will take the value of 2.7 because the lambda value is less that time, and we have to generate another equation like x1 is equal to some combination of x2, and we'll find this line, okay. So from here we can see that the points are like this, okay, and here we are getting a line which can represent both the points, okay. So PC is nothing but a function or a program by which we can convert a two-dimensional to one-dimensional, or from higher dimensional to less dimensions, okay, 3D to 2D or 2D to 1D. But here we have studied a 2D to 1D problem, okay. For 3D to 2D, you can go for other sources, okay. So here the main problem is to design the classifier and reduce the dimensions by using the PCA, okay. In LDA we will study that in linear discriminant analysis, okay. We have projected the points and find the separation between them. So how the lines are projected from 2D to 1D, that will be by using the algorithm that is called PCA. So that is called principal component analysis, okay. So we will go for analysis also, okay. So this is called the analysis part, okay, and the principal components are first PC and second PC. So for this class, I think that it will, the basics of the principal components are just convincing to the users, okay. So thank you.